Good afternoon and welcome to the Achieving Net Zero conference. My name is Tim Kruger. I'm one of the organizers of this conference, which is being co-hosted by the University of Oxford and Victoria University Wellington. I'm just going to go through a few logistics while the final few people are coming in. You should have access to Wi-Fi, either Eduroam or the cloud. No login is required for the cloud. There are no fire alarms tests planned for the days of this conference. There may be a test between 8:30 and 9, so if you're an early bird tomorrow before the conference starts at 9, you may hear that. If there is a fire alarm, please make your way out the exits there, out onto Holywell Street. This conference is taking place in two venues, here at the Holywell Music Room, which is the oldest purpose-built music hall in Europe. And also, this is where the plenary sessions are held and one half of the parallel sessions. And the parallel sessions are also being held in the Oxford Martin School just across the road. So there are volunteers here who will take you between those places. We are about to start the conference with an introduction from three speakers, but I'd like to give just a very quick overview. This conference runs for the rest of today, tomorrow, and half of Wednesday. And the Achieving Net Zero conference is about looking at the 2015 pledge from the Paris Agreement, which was to bring into balance sources and sinks of greenhouse gases within the second half of the 21st century. And the UK government has signed up to such a target by 2050. And it's clear that if we are to achieve the other ambition of the Paris Agreement of holding global mean temperatures between 1.5 and 2 degrees from pre-industrial times, we're going to need to do that globally, or to have a good chance of that anyway. So we have three speakers in the opening session. The way that each of these sessions is going to work is that we'll have speakers speaking for roughly half of the time of the session, and then Q&A from the audience. And so we have three speakers. Our first speaker, and I'll introduce all the speakers now, and then they can come up, is Amory Lovins, who is co-founder and emeritus chairman of Rocky Mountain Institute. And when I met him earlier today, I said, and you've been in this field for 4 decades. He went, well, actually, it's 5. Published his first paper in 1968. So he's got a half century of working in this space. We also have Miles Allen from Oxford, who's a professor of geosystem science and was one of the coordinating lead authors on the IPCC's special report on 1.5 degrees. And we have Rupert Reed, who's an associate professor at the University of East Anglia and is a spokesperson for Extinction Rebellion, which burst onto the scene about 10 months ago and has been highly effective in pushing for change in the way that we address climate change. Thought I'd plug a couple of his books. So This Civilization is Finished, copies from all good booksellers and also down here. And also he's been involved in Facing Up to Climate Reality. So no further to do, I'd like to introduce Amory Lovins. So Amory, if you could come up.
Good. Well, thank you for the honor of reporting some welcome surprises in the global energy and climate revolution. My public lecture tomorrow evening will include energy supply. Modern renewables now provide over 2/3 of the world's net additions of electric capacity, thanks to their powerful business case. But this morning, I'll focus instead on capturing modern negawatts. It isn't even morning anymore. Saved energy, 2/3 of it through better end-use technologies, are the world's biggest energy source, bigger than oil. If, for example, the United States total energy use had kept on growing in lockstep with GDP since 1975, Americans would have used that much energy, but instead cut that by more than half. And the cumulative savings are equivalent to 25 years of current usage. Meanwhile, renewable output doubled, very commendable, and yet with 30 times less cumulative impact than the savings. And renewables nonetheless get nearly all the headlines, the opposite of their effectiveness ratio. They're a very good thing, and we need them as well, but the headline ratio is the opposite because renewables are visible, but energy is invisible, and the energy you don't use is almost unimaginable. And yet saved energy is avoiding about twice as much carbon each year as renewable growth, and the potential savings keep on expanding. For example, around 1975, US government and industry all said that the energy needed to make $1 of GDP could never go down. A year later, I suggested heretically that it could drop 72% over the following 50 years. So far, it's dropped 58% in 43 years. Yet, just the innovations already added by 2010 can save another threefold, twice what I originally thought, at a third the real cost. And today, that's looking conservative, because optimizing buildings, vehicles, factories, and equipment as whole systems, not as piles of parts, can often make very big energy savings cost less than small or no savings, turning diminishing returns into increasing returns. There's a year-old peer-reviewed paper explaining that with a 4-minute video abstract. Just search on the title of the paper. And it explains why making energy savings several-fold bigger can actually cost less, because it doesn't use more but fewer, and it doesn't use fancier but simpler devices, but more artfully chosen, combined, timed, and sequenced. Metal ore bodies and oil reservoirs are finite and depletable assemblages of atoms, but energy efficiency resources are infinitely expandable assemblages of ideas, depleting only stupidity, which is a very abundant resource. Such integrative design let our Empire State Building retrofit save 38% of its energy with a 3-year payback. But then 3 years later, our cost-effective retrofit saved 70%, making this half-century-old government complex more efficient than what was then the best new U.S. office, which in turn is less than half as efficient as our own net positive, no mechanicals passive office in the coldest North American climate zone. And now there's a Bavarian building reportedly using 3/5 less energy than ours. Yet all these technologies existed over a decade ago. What's mainly improved is not so much technology as design, the way we choose and combine technologies. IPCC reported 5 years ago that the best European new buildings on the left and retrofits on the right, both with bigger savings towards the right, could save up to at least 90% of their energy use without significantly higher cost per unit of saved energy. The big vertical cost scatter just shows the size of the business opportunity from conforming inferior projects to best practices, because whatever exists is possible. Industry uses half the world's energy and electricity. My team's latest $40 or $50 billion worth of industrial redesigns have typically found energy savings around 30 to 60% on retrofit, paying back in a few years, and far outperforming the brown zone in the upper left, where most energy service companies deliver disintegrated design. Although there's another little brown dot for Crowley Carbon, perhaps the best of the ESCOs, which does better than most. In new factories, our projects have generally found 40 to 90% energy savings, with nearly always lower than normal capital cost. And some of the opportunities that we exploit are so simple, they've been simply overlooked. For example, in both industry and buildings, better design of pipes and ducts, saving 80 or 90% of their friction, could, if fully deployed, save roughly half the world's coal-fired electricity, with paybacks typically under a year in retrofit and instant in new builds. No magic is required. To wring out friction, we simply use big pipes and small pumps, not small pipes and big pumps. And to eliminate elbows, right-angle turns, and their friction, we lay out the pipes first, then the equipment, laying out supply pipes as if they were drains. We bend minds, not pipes. But this major opportunity isn't in any but one small engineering textbook. It's not in any climate model, government study, or industry forecast. Why not? Because it's not a technology. It's a design method. And few people yet think of design as a scaling vector, a way to make things big fast. Across all sectors, our 2011 study, Reinventing Fire, rigorously showed that even without integrative design, US electricity use could shrink a fourth by 2050, despite all-electric automobiles at a 2.6-fold bigger GDP. So that amounts to quadrupled electric efficiency, with an average cost below 1 US cent per kilowatt hour. It's a tenth of the average US retail price of electricity. And that overhang of unbought efficiency represents an existential but unpriced risk to current and planned supply assets. Integrative design only makes that risk even bigger. Integrative design can also make cars several-fold more efficient, making their later electrification faster and cheaper. Most of the energy needed to move a car is actually caused by its weight, and saving 1 unit of energy at the wheels leverages 5 or 6 units of fuel saved in the tank, because you don't need to waste 4 or 5 units delivering the energy to the wheels. This carbon fiber electric car, which I drive, reportedly made money from the first unit off the assembly line 6 years ago, because the carbon fiber that makes it so light was paid for by fewer batteries to haul less weight around, and then fewer batteries, of course, recharge faster. So the lightness offset the battery's weight and their costs. The integrative design compounds saved weight much faster than normally assumed. Assembly is radically frugal. It eliminates the conventional body and paint shops. It's much better for the workers, and the quadrupled efficiency, equivalent to 1.7 liters per 100 kilometers, makes no compromises and brings many advantages to the driver. Now, with marginal sticker price on the vertical axis and efficiency in US units, miles per gallon, on the horizontal axis, it's conventional to assess how much efficiency you can buy at what cost in automobiles by constructing technology by technology incremental supply curves. So the national academies in the US assessed it like this for cars and light trucks in 2002, like that in 2015, and eventually they embraced some previously rejected independent studies. But the actual design space is several-fold bigger than that. So I added 15 more data points, some from actual market platforms, from Honda with an internal combustion engine, from Toyota with the Prius hybrid drive, the BMW I just described, and actually the right-hand dot normalizes to the same test method used in the rest of the graph, a high-volume compact car production platform that we redesigned with a major automaker, ultralight steel models designed by Porsche Engineering for the steel industry and then approximated with a hybrid drive instead of internal combustion engine. And against the base units of an average car and light truck, we redesigned in 2000 with a British and a German Tier 1 an internal combustion and hybrid version of a carbon fiber SUV with its average car and light truck equivalents. And then there's a couple of others, but at any rate, you could see in that graph that most of the design space off to the right was not visible from the normal technology by technology design curves or supply curves. You can only see it by designing a whole vehicle. Now, in heavy vehicles, my team helped Walmart's truck fleet save half its fuel per case in a decade, including smarter logistics. But better technology alone can make US trucks at least 3 times more efficient, and airplanes 3 to 5 times, as in these decade-old designs by Boeing, NASA, and MIT. So the oil and gas reserves that are unsellable for competitive reasons now look bigger than the reserves unburnable for climate reasons. So oil owners are more at risk from market competition than from climate regulation. For example, the cost of getting US autos completely off oil has fallen from $18 per saved barrel 7 years ago to under $10 a barrel today, heading below zero in the next 6 years. So oil's becoming uncompetitive even at low prices before it becomes unavailable even at high prices. I'll summarize tomorrow evening a rigorous synthesis showing how to raise U.S. energy productivity threefold and carbon productivity, GDP per unit of fossil carbon, 16-fold, while saving $5 trillion, and that's on track in the marketplace. I'll also describe a Chinese government study showing how to raise Chinese energy productivity 7x, carbon productivity 13x, and save $3 trillion. And that strongly informed the 13th five-year plan that's now being executed by China. So if you extrapolate those and similar European findings to the other half of the world, it looks like that gets you to the Paris Agreement's 2-degree climate target about $18 trillion cheaper than business as usual. And if you invested part of that in natural systems carbon removal, that would get to about 1.5 degrees with trillions of dollars left over and huge progress on the Sustainable Development Goals. Making climate protection not costly but profitable ought also to simplify the politics. Now, climate science models conservatively understated the speed and the runaway potential of climate change. Climate policy models conservatively understated what we can do to stop climate change. Offsetting those two biases, what Jeremy Grantham calls the race of our lives, is very much on. Despair and complacency are equally unwarranted. Let me illustrate that with new data from a paper now in peer review. We need the non-fossil fuel share of energy consumption to rise and primary energy intensity, how much energy we use to make $1 of real GDP, to fall. And encouragingly, those have come along nicely through 2010 or so, but the progress was starting to falter, and the variables rates of change shown here were even trending in the wrong directions. But now we're starting to see pattern-breaking behavior since about 2010, with some early carbon mitigation signals emerging suggestively from noise as we look at the newer data. And I just put in a different way of showing energy intensity as well. There are some accounting issues that make two different methods both desirable. So this latest evidence through 2018 suggests that the past 3 years average for the spread between these two key causal variables now matches the 2-degree warming scenario and is trending towards the twice as tough 1.5 degree. Let me make this easier to understand. I just did it this way so I could show the regressions. By taking the reciprocal of energy intensity, so turn it in upside down, it becomes energy productivity, how much GDP you get per unit of energy used. These are, of course, all annual rates of change. So when we turn that, the magenta or yellow curve upside down, then it adds to the blue one, and the result is that up is always good. So you can see that something interesting is happening starting around 2010, but it's rather small, noisy data set. So let's look closer and see if it looks real when you look at the underlying causation. The International Energy Agency found that global energy intensity improved nearly a percentage point per year faster after 2010 than in the previous 3 decades that underlie most models. So the pace of savings has slackened in the past 3 years, causing IEA to bump up its targets for how much we need to do to get to 2 degrees. But we need to do only a little better than we actually did do in 2015. And in fact, 2014 to 16, energy savings entirely offset global economic growth, stabilizing CO2 emissions. Then on the supply side, nuclear in magenta stagnated, hydro kept growing, but look at all these new things happening, particularly since about 2010. In fact, the orange wedge isn't even in most models. It's the modern renewable heat that we just discovered hiding in IEA data. It's not in the BP database at all, and it's already about as big as electricity production from solar plus wind power. So it's producing 16 exajoules a year, 4.2% of global total final energy consumption. So some good news for a change. We're 4% further along than we thought, overlooked by most analysts and climate models. And then if you look at the annual changes, you can see there's this whole forest of stuff growing up since 2010 that's new and big and important. I think I will stop there, but perhaps in discussion we'll get into another nice thing we can do to slow the runaway carbon train by profitably abating methane emissions. And I'll just conclude with the notion that almost no integrated assessment models, the ones that convert climate science into consequence and choice, credibly analyze energy efficiency, which is the biggest contributor to climate protection. There's one very important exception. 5 quarters ago, Arnulf Grübner's IASA team published a low energy demand scenario that robustly achieves 1.5 degrees. It was featured in IPCC's 1.5 degree report. It saves about $1 to $3 trillion per year of supply side investment, greatly advances the sustainable development goals, and requires no carbon removal technologies. I hope my little provocations will help you imagine how even that impressive scenario could well prove conservative, significantly understating how much energy efficiency is now available and worth buying. Thank you.
Add my welcome to Tim's, and I'm really looking forward to the next couple of days. It's proceeding more or less according to script in that we felt we could rely on Amory to cheer everybody up. And so now my job is to depress you again before Rupert makes us all angry. I think that's more or less along that. So this wasn't the original plan for our opening session. We've been through many British politicians over the past few weeks. So I'm afraid the best we can do for our opening session is to give you a letter from our Prime Minister, which was sent around at the time of the UK's net zero announcement in the summer. And I want to draw your attention to one key phrase from this. I don't know if anybody in this room drafted this phrase, but the way Theresa May, remember her, framed this in that letter was ending our contribution to global warming by 2050 can be the defining decision of this generation in fulfilling our responsibility to the next. And I wanted to draw your attention to this because this is how one, I suppose we should say ex-stakeholder, framed the challenge of achieving net zero. And I'm going to talk in this talk from the perspective of the IPCC's 1.5 degrees report on what exactly that means. What does it mean to end our contribution to global warming? So one of the key sentences, in a tightly negotiated sentence, you can always tell when they've been heavily negotiated because they have sort of slightly odd words in them, like halt anthropogenic global warming. So reaching and sustaining net zero global anthropogenic CO2 emissions and declining net non-CO2 radiative forcing would halt anthropogenic global warming. The reason we said halt is because we were trying to convey the fact that this is what it would take to stop the warming on a time scale of a decade or two, but we weren't prepared to say exactly what you would have to do over the ensuing centuries to keep temperatures stable. Because, of course, that's a different problem. Stuff will be happening. We may have to keep pumping CO2 out of the atmosphere in the long term, but if we could frame the Prime Minister's objective in terms of halting global warming, that's what it is said it would take. And in here, so this is an animated version which Stuart produced of the SPM1 figure, which shows the different levers you have to pull in order to determine what level of warming you end up in. And crucially, the two big levers are the date of net zero CO2, or the total amount of carbon dioxide you dump in the atmosphere before temperatures stabilize, and what happens to non-CO2 radiative forcing. So in the far corner there's that lever you can pull up and down, which obviously affects the final temperature. But one thing we didn't do, and I can sort of update you on this, is to say exactly what we meant by declining net non-CO2 radiative forcing. We knew it had to decline But we didn't say, and it was, IPCC reports reflects the state of the literature at the time, but I think we could have been more precise on this, on the question of, well, how fast does non-CO2 radiative forcing have to decline in order to halt global warming? Well, first of all, this is back to a very simple scenario familiar to many of you. CO2 concentrations going up by 1% per year for 70 years, and then we just shut off emissions in year 70. And after that, we get stable temperatures, as you can see down at the bottom. That's emissions, concentrations, radiative forcing, and temperature. So zero CO2 emissions doesn't mean constant CO2 concentrations. It means declining CO2 concentrations, gently declining radiative forcing at about 0.3 per year. That 0.3 per year is actually set by the climate system's properties. It's what it takes to compensate for the long-term adjustment that would happen if you stabilized concentrations. So this is something that we've known about for many, many years. It just follows from these familiar climate system properties, the equilibrium climate sensitivity and the transient climate response that the IPCC has been assessing ever since the year 2000 or before. And what this means is there is a nice, unambiguous, simple relationship between radiative forcing and cumulative carbon dioxide emissions. There's a formula there if you like formulae, but if you're not really into this stuff and you just want something to take away in your head, try and remember 1 watt per square meter is roughly equivalent to 1,000 billion tons of CO2. So if some other activity is pushing up non-CO2 radiative forcing by 1 watt per square meter per decade, that would be equivalent to CO2 being shoveled into the atmosphere at 1,000 billion tons per decade. Conversely, and this is what a lot of people find it hard to get their minds around, if you have an activity that is reducing non-CO2 radiative forcing by 1 watt per square meter, that is equivalent to CO2 removal at the same rate. So this is what is driving the problem. This is CO2 emissions. As you probably think you've seen them, and other greenhouse gas emissions, as you think you've seen them many times before, but actually this is a new way of presenting these emissions. These lines on this stacked plot are all directly comparable to each other, thanks to Stuart Jenkins for producing this plot, because they all correspond to the CO2 that would have the same impact on climate and global temperature as the gas in question. So it's CO2, methane, nitrous oxide, the F gases, aerosols, and tropospheric ozone. Tropospheric ozone is the yellow one at the top. So all of these lines are directly comparable, and you can see if we just put the temperature on top there, the black line is the total of all of those colored lines. That's net greenhouse gases and aerosols, and the dotted line is the temperature response. So you can see that when we peak cumulative carbon dioxide forcing equivalent emissions, we peak global temperatures. So it's very easy to say what has to happen to emissions in order to achieve net zero, in order to stop global warming. This shows you just the derivative of the previous graph. So this is the cumulative emissions, this is annual emissions, and you can see that we need to get annual emissions of this aggregate carbon dioxide forcing equivalent emissions down towards zero by mid-century in order to achieve net zero. And that balance we see in the 2050s in these scenarios, these are the 1.5 degree scenarios, is with roughly net zero CO2 emissions and an approximate balance between aerosols, nitrous oxide and F gases on the one hand, and declining methane and ozone on the other. So that's what the temperatures look like, and you can see that basically to halt global warming, to do what Theresa May said we wanted to do, we need to get net CO2 forcing equivalent emissions to zero. They don't hit the zero line at exactly the same point, but you're then quibbling if you're arguing about that, because we don't certainly have a precise understanding of the carbon cycle or climate response to actually for that small difference to be meaningful at this point. So how long have we got? Well, human-induced global warming has just reached 1.1 degrees. That's according to Carsten's globalwarmingindex.org website, and is rising at 0.2 to 0.25 degrees per decade. That's a higher number than was reported in the IPCC 1.5 report. But before you rush off and say Miles admits it's worse than we thought, there's a certain amount of redefinition going on in here as well. So talk to me afterwards if you want to quote those numbers. And this means that we have, by simple geometry, a very well-defined braking distance, an amount of time we've got to get emissions to zero, which is just set by double the time it would take us to get to 1.5 at our current rate of warming. If that's not obvious to you, again, talk to me at the coffee break. But the point is, if we're approaching warming, if we're 10 to 15 years away from 1.5 degrees, we've got 30 to 40 years to get emissions, to get the warming rate to zero, to get cumulative CO2 forcing equivalent emissions to stop rising over that same period. So here are the simple messages to take home. We're now at 1.1 degree, warming at between a fifth and a quarter of a degree per decade. So that means we've got 15 to 20 years before we reach 1.5 degrees, or 30 to 40 years to halt global warming, if we want to limit warming to 1.5 degrees. The rate of warming is proportional to CO2 forcing equivalent emissions. And in your head, if you want to know what those are, it's just CO2 plus around 1,000 gigatons of CO2 per watt per meter squared for the aggregate effect of everything else. Every decade's delay at the rate we're going is following, and then followed by the same rates of reduction thereafter, adds another quarter of a degree. So mitigation that would now limit warming to 1.5 degrees would only achieve 1.75 degrees if we started in 2030. It would only achieve 2 degrees if we started in 2040. It's that simple. And I really hope these really, really simple messages will come out of the IPCC Sixth Assessment Report. IPCC Sixth Assessment Report authors, the challenge is in front of you. Okay, and the big question is, every decade's delay ratchets up temperature by another quarter of a degree. At what point is this an emergency? And that's my cue for Rupert, because that's the challenge we face, is another quarter of a degree doesn't itself sound like an emergency, but if we don't start thinking of this in those terms, we're just going to keep on adding more and more quarters of a degree. I hope that's a good way to lead into you. Thank you.
I have very little time. We have very little time. So let's talk about the present. What's happened this year? Well, you'll know the biggest thing that's happened this year. It's Extinction Rebellion. What happened in April proved that mass nonviolent direct action works. Before the rebellion, not a lot. After the rebellion, 63% of the British population agreeing we face a climate emergency. The environment leaping up ahead of immigration and the economy, according to opinion polls. In the latest poll now, 85% say they're concerned about climate. Mass nonviolent direct action works. Extinction Rebellion has 3 demands. Power has conceded something to each of them. The first demand is tell the truth. And the week after our rebellion, Parliament declared a climate and environment emergency. The third demand is citizens' assemblies, because our representative democracy has failed to rise up to this crisis. Citizens' assemblies to decide how we get to climate and ecological safety. And Parliament has now created a weak, but nevertheless, a citizens' assembly. And the second demand, and the reason I've taken that last is because it's the one most relevant to us here at this conference. The second demand to act now, in particular, halt biodiversity loss and go carbon net zero by 2025. And Theresa May has, for the first time, as we've heard, put in a carbon net zero target, albeit for 2050. So why 2025? Why not 2050? 2050 is death. It's death to the coral, of course. It's almost certainly death to the rainforest. And that's in due course almost certainly to most of us, or at least our children. And 2050 will be used as an excuse for prevarication and for geoengineering. Even so, why 2025? Why not something more realistic, like 2035 or 2030? Well, there are various answers to this crucial question. In my own opinion, the most important answer is the precautionary principle, which has been honored very much in the breach rather than in the observance, so far as these crucial matters that we're discussing at this conference are concerned. The precautionary principle is the main topic of my own research, And there are many reasons why the precautionary principle should be observed in the context which we're discussing here. A key reason is over-optimism in past models. We all know that various of the key things, such as Arctic ice, we've been led into complacency by years of false optimism. So I put it to you that the precautionary principle enjoins us to aim for the very most stringent target that we can imagine achieving. Here's another reason why we should aim for 2025. I don't know if you all have seen Tim Jackson's recent piece about climate models and climate targets. I strongly recommend it. It's a very short piece. Tim Jackson, author of Prosperity Without Growth. Jackson argues that it so happens that on a linear emissions reduction model, for achieving the carbon budget we should be achieving, now that there's hardly any carbon budget left, the most natural date for carbon net zero for this country comes out as, lo and behold, 2025. Of course, we all know that the actual date is not the most significant thing. What's much more significant is what's under the curve, the kind of curves that we've just seen from Miles. And most crucially, what's significant is front-loading our action, as Miles has just laid out to you very briefly. Of course, these considerations, and in particular the point about front-loading, accentuate the case for 2025. If we're going to achieve a very ambitious target, we need to start right now. So Tim Jackson disagrees with Miles, as do I. Miles said that his presentation would be the sort of pessimistic one compared to Amory's optimistic one, but I'm afraid by my lights, Miles's presentation is wildly over-optimistic. And here's a third reason for 2025, which is already implicit in what I've said, really. Simple urgency. We should aim for it. We should aim for the most ambitious target possible. For, as Antonio Gutierrez has said, if we're going to hit the emissions reductions necessary for 1.5 degrees in relation to 2030, and that's not even 2025, Gutierrez said last year that we need to start taking serious and adequate action within 18 months. So we've got about a year left. Do we know that we can do it? Do we know that we can hit carbon net zero by 2025? Of course we don't know that we can do it. But that's irrelevant in the kind of situation that we're in. It's irrelevant in a wartime mobilization style situation. Imagine a bunch of scientists being told to sit around in 1939 and try to figure out whether it was possible to defeat Hitler by 1945 or not. Would it have been prudent for them to have said, well, we can prove that we can do it by 1970? Is it physically possible? Well, of course it's physically possible. But here's the real question. Is it politically possible, right? Well, luckily that's our job. That's Extinction Rebellion's job. What Extinction Rebellion exists to do is to make what seems politically impossible politically possible. This is why it seems to me that the publication date of the Committee on Climate Change report at the start of May was particularly tragic for the authors of that report. The report was sort of dead on arrival, because if you've read the report, you'll know it says loads of things throughout it about, well, this is just about, within the bounds of what could be imagined as happening in this country, and this is what will be tolerated by consumers, and this is what producers can imagine being asked to aim for, and so on. And all of those assumptions suddenly the previous 2 weeks had gone out the window. As I say, according to the third demand of Extinction Rebellion, citizens' assemblies will decide how to get there, how to get to carbon net zero by 2025. But I put it to you that it's obvious that to achieve 2025, there's no pure techno fix. Significant chunks of our economy will simply have to be phased out. Well, why wouldn't we contemplate that? Well, we wouldn't contemplate it if we were addicted to the status quo. If we wanted to ensure that our society continues roughly like this for the foreseeable future before it potentially collapses. If we are serious about ending the utter recklessness of techno-industrial growth capitalism, we would contemplate rather what needs to be done and act accordingly. Now, in these remarks, I'm addressing, obviously, everyone in this room and everyone beyond. But I'm especially perhaps addressing my fellow academics. And I say this to you. People will believe you about the seriousness of this crisis if you get involved beyond doing science rather than if you don't. right? Scientists and others in the academic world are accustomed to thinking, well, we have to remain sort of neutral and we have to be seen to be telling the truth without kind of prejudice. So if we get too activistically involved, people won't believe us. It's the other way around with this issue. It's incongruent with an emergency to not get involved. An emergency changes the rules. Rather than activist involvement signaling bias, non-involvement tacitly signals bias against. It sends the covert message, actually, surely things can't really be as bad as my report or paper or whatever suggests. If you're convinced by the kind of thing I'm saying, what does such involvement require? Well, here's the good news. You don't need to get arrested with me next month. Any of you willing to do so, great, please come and have a word afterwards, a quiet word, but you don't need to do that. What's the first step? What's the thing that is reasonable to ask those of you who want to start putting your toe in the water? Well, I'd say that it's solidarity. Using your authority to lend authority to this most vital of causes. So how about thinking about something like this? Rather than just after a couple of days, us all going away and returning to our colleges and so forth, how about coming together and writing some kind of communique? There's a good old-fashioned word. Perhaps a letter to the Guardian. All of you who are legally permitted to sign saying, yeah, you know, we've talked about how to get to carbon net zero by 2050 or maybe sooner than that, but actually we want to go beyond that because we know that that isn't enough. And I'd urge you to take courage and inspiration from Claire Wordley and Charlie Gardner. I don't know how many of you saw this remarkable article in The Guardian last week. Headline, "We scientists must fight for our world." Claire is at Cambridge, Charlie's in conservation biology at Kent. This is how the article finishes. "We've taken a break from our usual areas of research to publish an article in the prestigious journal Nature, Ecology and Evolution, urging our fellow scientists to rise up and embrace rebellion. Scientists who have spent years telling policymakers we must change course, but they haven't taken action. They may be starting to do now, but only because people have engaged in open rebellion, making it clear that we will no longer accept inaction. Surely scientists have a moral duty to join the masses and rebel for life." I'll leave it here in case you want to look at it, or of course you can look at it online. That's the kind of thing I would love to see being supported coming out of this conference. I have very little time. So I want to say to you, what you're doing here at this conference is important, but it's not enough. I don't mean it's not enough by itself. I mean it's not enough for you to be doing. You need to be doing more, doing things of a different order. The next phase of Extinction Rebellion begins October the 7th in London and across the world. Extinction Rebellion is our best and perhaps our only shot. Let's not blow it. Join us. First step, individually and collectively, express public solidarity. Thank you.
Thank you to all our speakers. We've now got some time for questions, so from the audience. Just before I go to questions, just to let you know, in case you weren't aware, this is being recorded and live streamed at the moment. It will also be available subsequently. You'll sign things when you came in and got your badges, so it's okay by you. But just to remind you of that. So any questions, please raise your hands. Joe at the back there.
Thanks for the talks, and Miles, thanks for those clear messages. And we'll see. I'm on working group 3, so I'll throw that back to working group 1. But I did want to come back to the. We'll try and get some clear messages in working group 3 as well. Which actually brings me back to the other point. I think there's an awful lot of us in this room that live and breathe climate change. We do it as our day job. If we're doing IPCC, we're doing it additional to our day job. We're doing it in our weekends. We're doing it in our evenings. I don't know when I last spent a weekend not doing at least a little bit of work on climate change. Loads of us do public talks. You know, Miles is on the media a lot and was down at the children's strike. You know, I do it. Loads of other people here do it. We try and engage. I've been down to XR things to do, ask a climate scientist question times. And again, I'm sure many people in the room have. My problem at the moment actually is my job is harder because I am now having to defend the science not against skeptics, but against people who have heard Extinction Rebellion talks that are saying the IPCC is wrong, the IPCC doesn't include feedbacks when we do, the IPCC doesn't look at tipping points when we do. There's a lot of scary stuff in the IPCC reports. There's a lot of really hard, solid science that is really, really scary. So I would just say, I think we do, an awful lot of us actually do a lot and have been doing a lot for a long time, and it's not been as, maybe not as effective as we want. And Extinction Rebellion has been great on getting out on the streets and raising public awareness. But I would find my job much easier to do, going out and talking to the public and talking on the radio, if I wasn't having to defend my science against activists as well as against skeptics. So I hear your plea for us to get more involved, but I would also plea in return that when you say tell the truth, that's a really, really important message, and that's what we're all trying to do. And so I would just have the plea back that if Extinction Rebellion could actually get behind the science that we all spend an awful lot of our day in, day out trying to produce in our best possible way, then I think that would be just much more effective all round. So I hear your plea, and I totally agree for those who feel able to get more engaged. And sometimes actually it's because we as scientists aren't really trained to do that sort of thing. We're trying to do our bit. We've been doing our bit for a long time. But yeah, perhaps we could work better together.
Yeah, thanks. So thanks for that heartfelt remark. So look, it's a huge, complicated thing, which we could go into lots of different dimensions of. You say that the feedbacks are included and so on. I assume what you're referring to is, various of the small print in various of the reports. In terms of what gets into any of the headlines of the reports, let alone the summaries for policymakers, although I appreciate those are not your fault. The 1.5 degree report, there was in the headlines nothing about feedbacks. There's no sense from any of the news around the 1.5 degree reports of what's liable to be happening in the Arctic. So yeah, our argument in Extinction Rebellion is that the IPCC, as per standard scientific methodology, and part of my work in my day job is as a philosopher of science, and this is standard scientific methodology, is to lean on the side of conservatism. And that is the last thing that we need, when what we actually need to be is precautious. So there's a complicated discussion here to do with science, to do with politics, to do with philosophy. But I don't quite follow the logic of what you say. You say we're making your job harder, but I would have thought we might be just as easily seen as making your job easier. So traditionally what you've had you doing your job in the best way you possibly can, and then these utter, morons and shills and so on saying, no, the science isn't true. And then we're coming in and saying, well, actually, it's even worse than that. Let's pull it over this direction a bit. Why doesn't that make it easier for you to be the reasonable voices in the middle saying, oh, well, if we're getting criticized from both sides, then probably we're getting it about right. I don't actually honestly see what the worry is about how we're making your job harder. We're not, sort of undermining faith in science as an institution in toto. Well, I don't see that at all. What we're saying is, no, the science, the problem is the opposite of what's being traditionally said. It's not that the science is too alarmist. It's that, if anything, it leads towards being too conservative. And that is built into the IPCC methodology, I would say, in the way, for example, argued by Spratt and Dunlop in the What Lies Beneath report. It is to some extent built into the very methodology of science itself. And when you're doing post-normal science, as we inevitably are here in respect of climate, I think there's a heavy burden to be leaning more in the opposite direction, which is not just the job of the scientists. But you see the point that I'm trying to make.
Just very briefly, this isn't particularly on Extinction Rebellion, though. When US Democrat politicians say the IPCC says, or they always say the UN says, we have 12 years left, now 11 years left, to avert climate catastrophe, they're actually quoting a Guardian headline. But in 12 years' time, you can bet your life there'll be people out there remembering that and saying, the UN said the end of the world would have happened by now. And sort of, where's your credibility now? That's what I do struggle with. And, we are trying to push back on that. We are trying to help those politicians and understand what this deadline narrative means. But, when people say the IPCC says something which it didn't say, it is frustrating.
Yes, but my point is the opposite, right? My point is that saying we've got 12 years left to save the world is madly dangerous from the perspective of encouraging prevarication and building in a lack of precaution. So, you know, I'm totally not going to accept that line of argument, am I?
Great, good start to the conference.
Yeah. Good to see some energy in the room. Duncan.
Thanks very much. My name's Duncan McLaren from Lancaster University. I've got a question, and I'm going to comment on what just went. I think what worries me is that we're already seeing today as a debate about the accuracy and the presentation of science with accuracy. The most valuable thing in what we heard already from Rupert is that the moment is about politics. Climate change is a political and a cultural issue much more than it is, and it is a scientific and economic issue, but today it's political and cultural. So I was going to ask Amory particularly if that helps us understand why the promise of the efficiency measures that you talked about has so often not materialized and appears from the slides you presented to have been turned into a mechanism for growth rather than a mechanism that has allowed a reduction in energy use.
Yeah.
I'd like to answer a different question that that is more fundamental and goes to the previous topic as well. People concerned about climate are keen to inflict their climate understanding or their version of the truth on other people who may not share that view. But the great community organizer, Saul Alinsky, always said, talk to people where they're at, not where you're at. Speak to their concerns in their language. I would therefore urge all of us to focus on outcomes, not motives. There are many different reasons people might want to do efficiency or renewables or not treating soil like dirt, and therefore letting carbon come out of the air back into tilth where it belongs. And those reasons don't have to be the ones you care about. They don't have to be climate concern. People may want to save energy because of profits and jobs and competitive advantage, or because of national security or public health or a great many other reasons, or creation care, whatever it is you care about, that's all right. We can do the same thing for different reasons. We don't have to agree which motive is more important. We don't have to agree about all the reasons for doing it. Any one will do. And I think we often lose sight of that in our zeal to communicate our own passion, rather than allowing the same outcome to emerge from other people's passions, which in basic sense in a democracy are equally valid. So I think if we focus on outcomes, not motives, what often will appear as a source of gridlock and conflict can become a unifying project for most of the society.
But Amory, can I just press you on that question? Because I had the same question. Isn't the bottom line that for all your wonderful stuff about energy efficiency, which is so inspiring, that energy efficiency without a certain kind of political framework around it will simply produce, by way of the rebound effect, further economic growth, which will have resource depleting and destructive and polluting effects at other points, even if not through greenhouse gases, though I believe it will through greenhouse gases as well. In other words, isn't it just true that there is no purely free market economic panacea via technology for the problems that we face? And there just is no way that we're going to get there. No way we're going to survive unless we actually also have a severe framework of demand limitation on top.
I don't think that's correct. Rebound effects are real, except in very unusual pathological cases. They are very small. They're often so small that they're very difficult to observe. There's a large literature on this, Steve Sorrell and others have reviewed, and it simply doesn't support the notion that rebound is large. If it were, we would have seen much more of it. Of course, the the energy and the money you therefore save through efficiency can buy other things. If you understand how you made that money by saving energy, you might want to do more of it rather than less of it. You having done draft proofing and insulation in your house, you might want to put the savings into more efficient transport rather than helicopter skiing in the Alps.
You might.
So I think there is an important element of awareness of cause and effect here, but the general proposition that we need top-down limitations on activity in general because of a large rebound effect simply does not hold water. And it's actually an argument generally put forward by those in favor of emitting more carbon. So I'm rather surprised to hear it from you.
Thank you. This one can run and run, but can I just ask us all to thank all our speakers? Miles, very quick question.
Can I just have a very quick answer to Joe's point? I don't know what you're doing on Friday, the 20th of September, but you should be out talking to school strikers wearing one of these T-shirts, okay? And you can talk to Carsten, who'll give you a wave now if you wish to get your T-shirt. And Joe, this one's for you.
And what is
okay.
it?
Thank you very much. Just a little bit more logistics. That's the end of this session. This has been a plenary session. We're now going to split into parallel sessions. So if you want to go to the What Do We Mean by Net Zero talk, please go to the Oxford Martin School, just across the road. People will guide you in that direction, volunteers. If you want to go to the How Much Can We Reduce Emissions using currently available approaches, please remain in this room. That meeting will go until 3:30, at which point there will be, excuse me, at which point there will be a coffee break, which is taking place at the Anti-Chapter.
Introduce myself. I'm Sarah Darby. I lead the energy program at the Environmental Change Institute here, and I'm standing in for my colleague Nick Eyre, who is somewhere on a train on his way here, and he'll be with us, I hope, before very long. But anyway, it's a great pleasure to be here and to be able to introduce this session. The conference is, as you know, based on the Talanoa dialogue format. So we start off with where are we? Where do we want to go? How do we get there? So we're at that initial stage at the moment, and this session is looking at what can be achieved using the existing technologies that we have, and also using the ecosystems that we have, which are far more complex and wonderful than any technology we've dreamt up so far. But there are raw material to work with. So we have 3 speakers who are going to speak quite briefly. And if you have a question of fact that you'd like to raise very quickly after they've finished, that's okay. But for actual discussion, we're going to have a panel discussion when all 3 have spoken. And our first speaker is Zakia, and your surname is quite a difficult one. Sumoru. From Mauritius, but more recently from the Technical University of Berlin, who is a doctoral student there, looking with the chair of economics of climate change. And she's going to be talking about the special opportunities with islands to transition to zero carbon.
Thank you for the introduction. Thank you for listening. So I'm originally from one of those small islands, so there's a lot of personal stake involved here. But I also chose to look at the small islands because, first of all, they share a lot of common challenges, include narrow resource bases, small domestic markets, rapid urbanization, and very fragile environments. So on the left, you have one of the main narratives that small islands are pushing on the climate negotiation rounds, that, hey, we're drowning, we we face existential threats, but at the same time, on the technical and economic level, you have a lot of opportunities for rapid energy transition. And I look more broadly at the sector coupling of the energy and transport sector. And for the last year, I came to the realization that there's a great opportunity for those small islands to transition for a mobility transition, and that's and for that I use GIS and simulation tools to look at the limited road networks, the fact that there's high fuel costs and a need for direct grid storage solutions, which then leads to major cost savings, huge regional environmental benefits, and as well as we can combat the local externalities of congestion and air pollutions. So these small islands are mostly in the Caribbean. You have 5 like in the Africa, Asia, Indian Ocean area, and a lot more in the Pacific Oceans. And there are 57 of them, but I focus mostly on 3 representative islands by clustering them on different levels of economic development, degrees of isolation, and energy sector. And when I first started out, I dug very deeply into the history of transition or theories in general. And a lot of times transition look at how, when we look at energy transitions, they're very long, they're very long processes, such as from going from coal to oil or from wood to coal. And there's a lot of issues which slow down transition, such as the sheer scale and complexity, and the fact that we have a lot of locked-in path dependencies, and it's very hard. So once we have a locked-in, I'm sure you know it. So what I go is that I look at islands and I've connected them to the fact that we have niches versus regimes. Islands are excellent test beds, and the whole concepts that slow down transition, such as scale, market size, technological interrelatedness, and infrastructure needs, you don't have these on islands. And we also have the advantages of late adopters and, and the legacies of early pioneers. So with late adopters, you also have the externalities of learning, which small islands can then take on. And then the theories go on to inverse transition. And looking at this, we see that in the early 1900s, a lot of Latin American countries were able to transition faster due to the fact that they were all smaller economies. They had less natural endowments of fossil fuels, and this enabled them to leapfrog ahead by 30 years compared to bigger countries. And what I'm trying to say with it is that transition is not linear. And when we look at small island developing states and their primary energy consumption, it's much easier to come up with an energy system which meets all the demand on a scale that's easily more feasible. And these are my conclusions. As I said, the limited resources lead to less entrenched path dependencies and locked-ins as compared to the largest scale networks. And the isolated locations with their marked boundaries, you can very readily see the infrastructure, and this provides opportunities for location-specific change. And I then take these findings into infrastructure. So I think that in the mobility transition, infrastructure will either help lock in transportation in our already high carbon patterns or foster low carbon pathways. And this is kind of, it kills 2 birds with 1 stone, very non-vegan saying, I know. I'm sorry. Yeah. So, fuel is a big issue in small island developing states right now. They're very dependent on inputs imports. As demand has been growing, so has their fuel imports, and this puts a significant strain on their foreign exchange earnings, their public financing, and it leads to a vicious circle. So they spend more money on fossil fuels. This leads to less public money for going into renewable energy projects or infrastructure. And at the moment, most small island developing states spend between 6 to up to 20% of their GDP on annual fuel imports. However, a switch of conventional charging infrastructure to electric vehicles. So if we convert all conventional fuel charging to electric ones, and this is looking at 20 years in the future, this is so the amount is so minimal. So for example, in Fiji, you would be spending 1.5 for the next 20 years compared to there's an issue, compared to 10% of the GDP on a yearly scale. And you can also see that with our fleet simulation. So we looked at one feeder line from the main train station to kilograms of CO2 equivalent per day, and also converting the private fleet also leads to lots of savings. I'm not going to go into it, but feel free to ask me afterwards, because my main message is that electrification of the private fleet is not the answer. We have to look at tourism, and that's because tourism is huge on these small island states. It leads to it contributes to 50% of GDP and jobs, but at the same time, it's a very big demand on our infrastructure, energy, and can also lead up to 80% of carbon emission on islands such as the Maldives and La Réunion. And what I found in my research is that there's a link between tourism and rural transport, and most of the islands, they followed this path of land use development. And you can see that there's a huge urban corridor where up to 50, or in some islands, 90% of the population live. So tourist demand has no effects of of the urban transport. However, because points of interest are so spatially diverse, there's a nice link between tourism demand and optimizing rural networks. And what I'm trying to do now is look at routing networks as well as last feeder miles. This is my methodology, and I'm very interested to know what you think about this and if you have some feedback. I didn't have any results yet, and I think this is a very interesting research at the moment, because there's a lot of current developments and solutions going on in the island. So Barbados is the third highest electric vehicle user in the world at the moment, whereas Mauritius is following in the footsteps of Singapore and trying to introduce mass transit lines through the urban corridor. And I think that if you have sort of a cookie cutter pattern, you can kind of help enable these islands to instead of going through different cost benefit analysis, just to share ideas and therefore speed up the transition. So these are my next steps. And I also think it would be great to see whether, if we offset all these carbons from tourism on their in-road travel, to see what would the effects be on flights. Tourism is increasing at the moment, more people are flying, and how can we help decarbonize that? And well, my takeaways are, I think that when we look at topology, small network effects, and tourism together, they provide a unique opportunity. And I think we should focus on optimizing public transit and introducing database solutions. Thank you for listening.
Great, thanks very much. So I'm going to talk about some work that has been done under something that's called the One Earth Initiative. This is an initiative of the Leonardo DiCaprio Foundation, and these are the goals of the initiative: 100% renewable energy, 50% lands and oceans protected, and net zero agriculture by 2050. So the part I'll be talking about is some small part towards working towards how we would get 50% lands protected and the what that would deliver to a net zero pathway. So the first part of the work that has been published is in this book here, Achieving the Paris Climate Agreement Goals. It focuses on the global decarbonisation, so 100% renewable energy delivery by 2050. And it's a very detailed model on the energy side, looking at 72 regional electricity grids and spatial analysis of the infrastructure possibility for that to deliver that. In terms of the land use side, so because this work puts forward a pathway, a modelled pathway for 1.5 degrees, including that 100% renewable energy, but even with that level of decarbonisation, there's still a requirement for some amount of carbon dioxide removal. So not going to explain all of this graph to you, but the part that this presentation will focus on is the land restoration, where we're removing 400 gigatons of CO2 by the end of the century through what I'm calling ecosystem-based pathways. One of the points in this graph showing is that we've got a buffer in there, so it's not actually showing that the terrestrial land sink has reversed and become a source by 2030. Can you see so sorry, you can't see the years at the bottom, whoops, because of the size of the screen. But we have 2020 about here, and the end of it is 2100. Sorry, the years are missing. But anyway, the land sink is not reversing there by 2050. It's just a built-in buffer that has been recommended now by the IPCC that we assume 100 gigatons CO2 of feedback from the land system, so that we're being very conservative, that those feedbacks, and anyway, there's more to describe there. So this is, again, not very clear, but this is the point to take from this chart. We've got a baseline scenario, which is the sort of flat blue line in the middle. That's actually RCP, what it says down here, RCP 2.6 and 1.9 from the reference scenario, which is the blue flat line in the middle, is based roughly on the message glow biome RCP 2.6 scenario under SSP2. So that's the reference scenario. And then we have a 2-degree pathway, which is the next line down, the sort of light blue line, and that's using, out of those 400 gigatons CO2 removals, about a third. Whereas the 1.5-degree pathway, this is in terms of the removals at the bottom, needs all of that restoration, which was all of the restoration potential that this particular exercise found. So even with a huge level of decarbonisation, the removal potential is quite large. So the purpose of this study, one of the requirements or the objectives in the study was to achieve the level of carbon dioxide removal required without any reliance on what we termed risky and undeveloped technologies. So geoengineering, nuclear, bioenergy with carbon capture and storage, so none of those have been included. So therefore, the focus has been on how to achieve this scale of removals through land use or ecosystem pathways. So these are the pathways that were looked at. In this graphic here, they're divided into 2 global biomes, so tropical and subtropical on the one hand, and temperate and boreal on the other. So there's actually 4 pathways here divided each into 2 biomes, so it looks like 8. So the largest potential we're seeing here is from reforestation, and this is the larger potential is in the tropics and subtropics. So what we've done here is phase in the restoration pathways, and then they phase out as sink saturate. So in the tropics, we have much higher peaks, but much shorter time period that restoration the sequestration is being achieved over. And in the temperate and boreal, there's there's much slower sequestration pathways. There's actually numbers attached to all of these pathways, which I can't see because they're in my notes. Off the top of my head, they are So in terms of annual sequestration, the peak here is around 9 gigatons CO2 around the middle of the century, 2040. And we're looking at about, for example, agroforestry down the bottom is around 1 gigatons, 1 gigaton CO2 sequestration a year, and reforestation globally is around 6, I think. But so that's the kind of scale of the numbers in there. So what I wanted to really focus on and describe to you is so looking at the technical sequestration potential of enhancing land-based sinks doesn't tell us a lot about how we would go about doing that or whether it is really doable. What's actually important, and there are several studies showing very similar magnitude in terms of sequestration potential from what's being called natural climate solutions. So we can all do that ad infinitum, but what I think is much more interesting is looking at the land management and governance decisions and choices that would need to be made for those pathways. And that was what was quite different in this study, and I think is what is important about it. So I'll spend a few minutes going through this chart, and again, there's a fair few more numbers attached to it that I'll have to try and remember. So firstly, the forest ecosystem, actually the first thing to say about this is it's a prioritization of land management pathways. So the first priority is that emissions from land use change, here where we have our yellow anthropogenic emissions, go from a source to a sink. So we're ending land use emissions. There's ending deforestation and degradation by 2030 is the assumption built in here, as well as conversion of peat and also major restoration of peat to end those emissions. So that's the first priority that's not on this chart because we're talking here about removing carbon dioxide. So the second priority after ending land conversion is restoring ecosystems. Forest ecosystems is what we looked at here. And the assumption that was made was that 25% of what the FAO, all of this is based on FAO categories, land use classifications. So 25% of what's called other natural forests are set aside for conservation. So that's sort of assuming that logging in those natural forests is ended, and doing that combined with currently something like 30% of forests are primary forests. So if we set aside 25% of what are not primary forests, we would bring the total of sort of set aside and potentially conserved forests to 1,900 million hectares, I think, which is roughly 50% of current global forest cover. So working towards that idea of 50% of natural ecosystems protected. That's what this is based on. So the second priority after restoring, there's a few other things I wanted to say on that just quickly. The sequestration rates are assuming that logging hasn't happened in the last 20 years. So essentially to make sure the sequestration rates are additional, we assume that post-logging sequestration happens, we don't count that, and then we're just looking at the transformation of a degraded forest to a mature intact ecosystem, the carbon sequestration there. So reforestation, then this is based on the assumption of the assumptions are based on the Bond Challenge, which is a political target for 350 million hectares of forest to be restored by 2030. And unlike what countries are actually pledging under the Bond Challenge, which includes a lot of plantations, we are assuming here natural forest restoration. So natural forests are extended through potentially passive restoration that's focused on buffering and connectivity for existing primary forest ecosystems. So again, it's increasing ecosystem resilience and spatial extent. And the important thing here is the level of land use change here, like in all of those pathways shown and all of this sequestration, this is the only land use change, 350 million hectares of extra forests. That's in line with a planetary boundaries threshold, suggests we need to maintain at least 75% of our original forest cover, which we're not quite at, we're a little below that. So around 400 million hectares of extra forest would be good. Beyond that, or even that amount, that's a lot of land. But going beyond that amount of land, for example, there's recent papers suggesting 900 million hectares of reforestation, starts to bring up a lot of problems in terms of land use change management. What are those lands currently used for? So really the idea here was to minimize the amount of land use change required. Just to finish up quickly, lower down the priority then is sustainable use of sustainable forestry, sustainable agriculture. So this sustainable use of forest pathway was based on a lot of studies now showing the potential to reduce forest harvest and increase rotation times, resulting in some reduction of timber harvest, but not massive reduction. So halving the harvest and doubling the rotation times would maybe result in a quarter, 20% or 25% of reduced timber harvest, which again has many governance implications, but is potentially doable. The latest FAO set of the forest report showed us that we're actually producing timber products much more efficiently now, needing less timber to do the same amount of things with timber products. Agroforestry, we just used very conservative assumptions there, above ground carbon only, 20%, I think, 300 million hectares of global agricultural lands. And again, we removed a baseline of existing sort of growth in trees on farms from the sequestration potential. So we got very conservative numbers. Just to wrap up, I wanted to make this point. It's hard to bring it all into such a short presentation, but this is not my work, a paper last year from Garnett and team, and it mapped the overlap between Indigenous managed lands and global protected areas, showing that 40% of remaining protected areas and biodiversity, high biodiversity conservation areas are under Indigenous land management. The extent of community held and collectively managed lands is actually much greater than that, than the 40%, than the area shown here. I think they're showing a quarter of the world's land surface is under Indigenous managed lands in this study, and that intersects 40% of protected areas. If we extend the tighter definition of Indigenous held lands to collective and community land management, it's something like 60% of the Earth's surface. And the potential there, the crossover between respecting and recognising Indigenous land title and ownership and allowing and having legal recognition of that, and the potential for restoration of degraded lands is very large, and it can be quantified, it can be included in models, it can be brought into this conversation. I actually had a quote here from the recent global assessment from the Intergovernmental Panel on Ecosystem and Biodiversity Services, make the point that Indigenous knowledge, systems, values, sort of world viewpoints are not included in the global climate models and in the conversation about climate change. Thank you very much.